In a previous lecture, we discussed how a tandem MS spectra can be analysed to reveal the amino acid sequence of a peptide. But modern mass spectrometers can generate thousands to tens of thousands of MS spectra from a single sample, and this makes manual de novo sequencing completely impractical for all but a limited number of cases. As tandem MS spectra are simply a list of numbers, we can use computer algorithms to analyse them. So what data does the mass spectrometer actually produce? This image is taken from an AB-SciX quadrupole TOF machine, but data from other manufacturers looks essentially the same. Every half a second, the instrument scans a mass range, in this case 350 to 1500 Daltons. This is an MS scan and shows all of the intact ions that are being sprayed into the mass spectrometer at a particular time. The intensity of all of these ions is summed, and a point is plotted on the total ion chromatogram, or TIC, indicated by this line. The computer then analyses the MS scan looking for ions that are separated by half a Dalton or less, indicating that they are multiply charged. The C12 isotope of each multiply charged peptide is then selected and fragmented, resulting in an MS scan for each multiply charged peptide, as shown in this list, of which you can only see part of it. But for all of the sequence of the peptide, for determining the sequence of the peptide contained in each MS scan, we don't need all of this information. We can simplify things by converting the data from the mass spectrometer into a peak list. This generic simple format, often referred to as mascot generic format after one of the database search engines, looks like this. Each intact peptide selected for fragmentation has the beginning and the end of its list defined. The intact peptide mass is noted, as well as the charge on the peptide. In this case, the peptide was doubly charged. The fragment masses detected from fragmenting the peptide are then listed, along with the intensity and the charge state of the fragment. This is repeated for all peptides fragmented in the sample and stored in the data file. This is the data that we can now search. Because we know the masses of carbon, hydrogen, nitrogen, oxygen, and sulfur, the elemental components of the majority of amino acids, we can calculate the mass of each amino acid. Once we know the masses of the amino acids, we can calculate the mass of peptides by adding together the masses of the amino acids in their sequence. We can also calculate the mass of fragments that would be generated from the peptide by adding up the amino acid masses in the fragment. So this leads us to the idea of why don't we make a database of all of the possible peptide sequences? The problem with this is that you make the search space absolutely enormous, and the time to search that space becomes days to weeks, even with supercomputing. This is because you have to generate a theoretical peptide of all possible lengths with all possible combinations of amino acids. If you set a minimum peptide length of 5 amino acids, the first in the list would be this peptide, 5 alanines. Then you would have to have 19 more sequences where the first amino acid is changed to each other amino acid, and you have to repeat this for the second amino acid position, and so on. It has been calculated that an 11 amino acid peptide can have 2 times 10 to the power of 14 theoretical peptide sequences. So it becomes obvious how large the search space becomes. We can restrict this a little by saying we only want tryptic peptides, sequences generated that end in lysine or arginine, but this still generates an enormous number of peptides. So another approach was thought of. In 1994, Jimmy Eng and John Yates published the solution. Prior to 1994, mass spectrometry was not being widely used for characterizing peptides, but when it was, it relied on a database of spectra to match patterns. This approach has been used since the early 1980s to characterize simple simpler chemical molecules, and is still the identification method of choice for those working on small molecules. But generating a spectra from each possible peptide is just as impractical as building a database in the method described in the last slide. Jimmy and John realized that rather than search amino acid sequences that may or may not exist, they would search a database of sequences that had already been determined by gene or genome sequencing. At the time, this was a relatively small dataset comprising mainly of translated gene sequences deposited in the NCBI non-redundant database. But it reduced the search space of tryptic peptides to 1 by 10 to the power of 8, or 1,000,000 times smaller. This could be made smaller by restricting the search space to a particular species. So how does this work? First, we need a database, such as the Uniprot protein database. You can see that this database has a lot of entries. Each entry has quite a great deal of information about the protein, but we're only interested in the sequence data. The sequences become the basis of our search because we can theoretically cut the sequence at lysine and arginine and generate theoretical peptides, which we can then calculate the mass of. Using the example of myoglobin, the search algorithms can turn this into this, and this happens for every sequence in the database. Once we have the sequences of these theoretical peptides, we can calculate the mass of each peptide by summing the amino acid masses. We can then calculate the masses of the fragments that could be generated if the peptide was selected for fragmentation. The software will repeat this for every protein sequence in the database, making a list of theoretical peptides and their calculated mass, and then calculating the mass of the possible fragment ions that could result if the peptide was fragmented. We're going to swap example peptides from myoglobin and use this second tryptic peptide. The peptide has an intact mass calculated from the amino acid sequence of 1605.8 Daltons. If ionized by MALDI, which produces predominantly singly charged ions, the mass detected by the mass spectrometer is 1605.8 plus a hydrogen ion. While the mass in electrospray, which generates multiply charged ions, is 1605.8 plus the 2 hydrogen ions, one which attaches to the C-terminal amine, the other one which attaches to the side chain of the C-terminal arginine. From the amino acid sequence, we can tabulate the theoretical mass of fragments that would be produced from the intact peptide. For example, if one molecule was fragmented and broke through the most C-terminal peptide bond, the arginine would be released. In the MSMS spectra, we would observe an ion of 175.1. If another molecule was fragmented and fragmented through the second last peptide bond to release isoleucine and arginine still joined, we would observe another ion at 288.2. If another molecule was fragmented somewhere in the middle of the peptide, producing this fragment, we would observe an ion at 1008.5. We have now created a table of theoretical masses. Now we need to see how well it matches the raw data. So a peak list was generated from the raw data file from the mass spectrometer, and this is one of the peptides in the data file. The mass of the intact peptide is 803.9 Daltons, and it is a doubly charged ion. When we submit the peak list to the search software, it will generate its theoretical peptide list and then look at the entries in the peak list. The software will note the mass of 803.9 Daltons and convert it to its uncharged peptide mass of 1605.8. The software will then take the theoretical peptide mass list and make a sublist containing the theoretical peptides with a mass of 1605.8 Daltons plus or minus an error tolerance, in this case about 0.02 of a Dalton. This sublist may still contain hundreds to thousands of theoretical peptides, all with different sequences, that will all have a mass of about 1605.8, give or take 0.02 of a Dalton. One of these peptides will have this sequence, and this is the table of its theoretical fragments that could be produced if the peptide was fragmented. The software then starts matching numbers. So the 175.1 is the mass of the C-terminal arginine, 228.2 is the mass of the C-terminal isoleucine arginine fragment, and 401.2 is the isoleucine leucine arginine fragment. So the software tries to match as many ions as possible in the peak list to the theoretical masses in the table. The theoretical peptide with the most matching masses, shown in the red text, is the most likely match. The search algorithm can calculate an ion score based on how much the table is filled in and reflects the probability that the match is not a random event. The algorithm also calculates an expectation value that is analogous to a p-value, where a value of 0.05 means that the match has a 1 in 20 chance of being incorrect. So the lower the number, the more likely the match is correct. The scores also depend on the numbers of candidates being considered within the error tolerance, or the search space. For this particular parent ion, there were a number of matching sequences with a good score. In fact, the top two hits have identical scores, and a look at the sequence reveals why. Leucine and isoleucine have exactly the same mass. They are isobaric. Thus, from the data, even with a complete series of B and Y ions, we still would not be able to tell which one of these peptides is the match. We would have to decide which is correct from other identified peptides in the sample. Once the MSMS scans are each assigned to a peptide sequence that is most likely, the peptides belonging to the same protein are grouped together, and the protein with the largest number of high-scoring peptides is at the top of the list. In this case, horse myoglobin is the top hit with 19 matches, but only 9 of these are deemed significant, having an expectation value of below 0.05. The peptide matches that are not deemed significant are included because, although on their own they do not provide enough evidence, when collected with the other significant peptides, they strengthen the identification. The second hit in the list was also myoglobin, but from the rabbit. From the total number of peptides identified in the data, only 11 match this protein, and only 4 of those are significant. But all of these peptides can also be assigned to the horse myoglobin, plus 7 more, so the horse myoglobin is more likely to be the correct identification. The interesting thing about this rabbit myoglobin is that it has our peptide containing the leucine rather than the isoleucine. And this provided the theoretical peptide sequence that is equally likely from the data. Just to close this part about data searching, we examine this figure from a 2010 paper which summarizes how searching works. The MSMS spectrum acquired by the mass spectrometer is turned into a peak list. When submitted to the search engine, the software takes a protein sequence database and turns each protein sequence entry into a list of theoretical peptides and theoretical MSMS spectra. These are then compared, and a ranked list of possible peptide matches for that one MSMS spectra is created with each peptide receiving a score. To work out the expectation value for the top scoring sequence, we plot the frequency of scores and then calculate how far outlying the top score is, and this is what is reported. This is repeated for every MSMS scan until as many of them as possible can be assigned to a peptide sequence.